I'm Bob. I'm back. Here's part 2 of Chapter 4, Part B. Where do electrons actually hang out? Now, in the first part, we looked at the idea that the electron's address system is made up of 4 quantum numbers. You might remember those. You might think about the principal energy level, the N, the angular, what is L, the letter L, that's the shape of the region that we're in, and then the magnetic, which is the letter M, which is the orientation in space. There's one more that we got to look at. But as we look at the principal quantum number N, we know it's the principal energy level, where N equals 1, 2, 3, 4, and so on. Okay, now, that being said, ladies and gentlemen, we can also continue looking at the quantum number, the azimuthal quantum number. You might look at it as the sublevel quantum number, but you might remember it more easily as letters S, P, D, and F. Now, for example, these values, I would be looking at S, P, D, and F. That's what I would want you guys to remember. Okay, now here we looked at the shape of this sublevel orbital. So remember, the orbital is the region where the electrons hang out. Okay, they have different shapes. That's where the S, P, D, and F come in. Now, are there some others beyond that? Yes, they are outside of what we are covering here for chem, but you can see through this picture here, like we went through the last time, these shapes, they go really woo. Okay. We also looked at the idea of how these, we look at the principal level, and we notice that there's one sublevel. We look at the second level, there are 2 sublevels. We look at the third level, and you notice there's 3 sublevels. Fourth level is 4 sublevels. Okay. And if you look at the, and then so on and so forth. Okay. We looked at the magnetic quantum number, where we're looking at the spatial orientation. We talked about the idea of taking a marker like this, and here it's arranged on its side, and here it's arranged on, standing straight up. And then, of course, here we're looking at it straight at you. So that would be like the z-axis. Here's the x-axis. Okay, it's going across x, y, and z. So in our picture over here, you can see our hero Ash Ketchum from Pokemon fame. Same figure, spatial orientation, different. He's in a different position. Just like our 2x, 2p in the x direction, 2p in the y direction, and 2p in the z direction. Okay. Don't worry about why are there 3 of these 2p whatevers. Don't worry about that at the moment. Just understand that there's different magnetic quantum numbers. In other words, how is the thing arranged in 3-dimensional space? And that's what you got to worry about. All right. Now, there is this dude named Pauli. That's this guy down here. Hey, dude, how you doing? Hey, let me shake your hand. Oh, you're just a picture. But he did come up with an idea. And the idea was this. The Pauli exclusion principle says that there's no 2 electrons in an atom that can have the same set of 4 quantum numbers. Whoa. What are we talking about here? Here's the idea. You can't have 2 electrons occupy the same level, the same sublevel, same spatial orientation, and be in the exact same spot at the same time. Okay, so what does that mean? The maximum number of electrons in any sublevel section, like 2p in the x direction, 2p in the y direction, 2p in the z direction, is 2. That's the maximum they can have. And they have to spin in opposite directions, like this. So one's got to spin clockwise, the other's got to spin counterclockwise. Yup, that's the way it works. Now, The electron spin quantum number. This is MS, and I'm more interested that Honors Chem know the name of this, the electron spin quantum number. Okay? General chemistry. What do I want you to know? Electrons spin opposite of each other. You'd say, but wait a minute, why would we need to do that? Okay, well, there's a notation for that. Why is it the electrons are spinning opposite of each other? There's a reason for it. But if we look at the idea of an electron, kind of like a magnet, okay, and you can see here we got a south and a north and a south. We know that if you put north-north, they're going to push away from each other, right? They're going to push away. Now, if it's north-south, they're going to attract. Like Paula Abdul, opposites attract, just like I mentioned in class. Yeah, see? Yeah, you can see right here, ladies and gentlemen. Look how that works out. Now, the designation, Honors Chem, you're responsible. There's plus 1/2 and minus 1/2. Okay? Now, why those designations? They have their reasons. Okay? But one, the plus 1/2 means the electron is spinning counterclockwise while the other electron has a negative 1/2 and is spinning clockwise. So it's like this. They're spinning opposite of each other. Okay, so there's two possible values. All right, plus 1/2 and minus 1/2. But again, that begs the question, why are the electrons spinning opposite of each other? Well, each orbital can contain only one electron with each kind of spin. Okay, so for example, let's go back to 2p in the x direction. Just look at 2p in the x direction. Remember, x is the horizontal. Okay, that means you have one electron. The most it can take, the most number of electrons 2p in the x direction can take is 2 electrons. Now, those electrons have to spin opposite of each other. Okay, and if you think about it, Morpheus has got our answer. What if I told you electrons spin opposite of each other to stay stable? Ooh. Whoa. What? Right. Dude, Morpheus, let's try that again. What if I told you electrons spin opposite of each other to stay stable? That's a pretty important idea. So they got to do this in order for no kaboom! Stability. And atoms have to have stability, okay? You have neutrons there in the nucleus with the protons to keep the nucleus intact, right? But the electrons need stability too, because remember, electrons, they're not opposites, right? They're alike. They want to push each other away. But when they're spinning in opposite directions, they're a lot more stable that way. Whoa. Stability is kind of an important thing because it allows us to stay in one piece and allows us to live. Okay. So the quantum model subdivides all but the first principal energy level into sublevels, which are assigned these L values. What L values are you talking about? Remember the SPDE, the SPDF, okay? On level 1, you only have one sublevel. That's S, end of story. Wait, you're thinking, why just the S? Why not the P and the D and the F like all the others? That's because it is the closest to the nucleus. So there is the tiniest amount of room around the nucleus. So there's not that much there. I mean, it's kind of like taking a balloon and you blow it a little bit. There's not a lot of space around there. But if you keep blowing it, it gets bigger and bigger, which means more sublevels can go in. Okay? So if we look at it, each level is split into sublevels. They're assigned these L values, which we call S, P, D, and F. Now those sublevels are subdivided again into orbitals assigned M values. Well, wait, what's the M value? The orientation, the X, Y, and the Z. We're just going to stick with the basics here. And then each orbital may contain up to 2 electrons. And the little s that you're seeing down there is the spin of the electron. You know the real kicker about this? This is true for every single atom that's out there. Even the atoms that make up you, your mother, your daddy, your sister, your brother, your dog, and your neighbor, and your chemistry teacher. Yeah! That kind of consistency in creation is just a testament to the God who made it all. I'm just saying, don't hate the player, hate the game. All right, let's talk about the S sublevel. Gen Chem? Yeah, you need to know this. Now, the probability plot has a spherical shape, like this. Okay, so level 1 sublevel S has a spherical shape. Now, is there a level 2 sublevel S? Yes. Level 3 sublevel S? Yes. Level 4 sublevel S? Yes. Okay, but let's just look at the S sublevel. It's a nice, cute little sphere, isn't it? Now, what's the maximum number of electrons that can fit in there? Well, according to the Pauli exclusion principle, 2. 2 is the maximum you can fit. All right, let's look at the P sublevel. Now, we have these 3 dumbbell-shaped orbitals, 1 on each axis, okay? So let's sift over here. Now, if we look over here, you kind of notice here's P in the x-axis, here's P in the z-axis, and here's P in the y-axis. Now you'd say, well, what's that? That's the 3, the P and the x, P and the y, and P and the z, all combined into one thing. You'd say, but wait a minute, what is that thing there in the center? Right there where my arrow is pointing. Wait, I don't see the arrow. Right where the red beam is pointing. Okay, I don't know if you can actually see the laser beam, but we'll find out. Hey, that, ladies and gentlemen, is the nucleus. That's the nucleus of the atom itself. And then, of course, the D sublevel. 5 different orbitals. Check those out. And they have their own arrangement as well. Up to 10 electrons can hang out. 2 on each one of them. 2 in here, 2 in here, 2 in here, 2 in here, and 2 in here. 2, 4, 6, 8, 10. Now, are there always going to be 10 electrons in there? No. Could it be? But that's the maximum we know that's there. Okay, it's focusing. Focus. 10 electrons. That's the D sublevels. Oh, my Lady Gaga, there's the F sublevels. Ooh-wee, and it's getting weirder, man. We're talking Twilight Zone. 7 possible orbitals, up to 14 possible electrons. You'd say, well, wait a minute. You said that the D could take up 10 electrons, right? Because you had 5 different ones. 5 different of these possible sublevel orbitals. And now the F, you've got more. You've got 7. So each one takes up to 2. Yup, that's it. So you can see energy levels and occupied sublevels, you can see all right through here. Okay. Okay. We're going to fly through here, allowed electron capacities of energy levels. So this can tell you, if you look at this, look at how many electrons can actually go through. Can be loaded up on each of these sublevels here. Okay. Now this is kind of like a computerized image. This is a computerized image right there. Okay. Yeah, just look right there. Yeah, look right there. No, you gotta look that way, that way, that way. No, that way. Yeah, that way. Yeah. Okay. I'm running out of time here, guys. So this is just showing you that the higher the level you go, the bigger it gets. So that's 1s, 2s, 3s. The sublevels are ranked by their relative energies. Okay, I gotta stop. Bye.